Hello again and welcome back to Thinking Maths. Up next is the final installment of our exponent laws, the fractional exponent law. Now how it's written when you have a base to a power that's a fraction, in this case a to the m over n, I always tell my students the bottom number goes into the notch. So a to the m over n is the nth root of a to the m, but it can be written a second way as well, as the nth root of a, and that whole thing is to the power of m. Let me show you what I mean with the next example. So the example I have written here is 8 to the 2/3. Now we can write it in either of these ways, and which way depends on what we have to work with, but I'm going to show you both ways instead. So we have the cube root of 8 squared. Now, if you wrote it this way, we can square the 8 first to get 64, and the cube root of 64, since 64 breaks down into 4 times 4 times 4, it's just 4. We also could write it the second way here. I could take the cube root of 8 all squared. Now, the cube root of 8, well, 8 itself is 2 times 2 times 2. And a cube means I need this number of items before I can pull it out from the radical sign. So being that I have 3 2's here and it's the cube root, I can replace this whole expression with 2, and 2 squared is 4. Okay? It ends up with the same answer. Now you might ask yourself, well, that's all well and dandy, but when do I use which one? Well, my suggestion to you is, well, my answer is actually it depends. If it has a perfect cube or fourth or whatever number this is, I would write it in the second way first here. So if it was the fourth root of 16, well, 16 has a fourth root of 2, so I would write it this way. Okay? But if it didn't, I would err on the safer side and go with this first law instead. So it kind of depends. Let's take a look at a few more examples and see if we can hammer this out. Now the next example I have here is negative 27 to the power of 2/3. Now I know this is a page dedicated to thinking math, but thinking's great, but you do have to have some basic skills first. Now, one of those is knowing your perfect squares and your perfect cubes, at least to a certain number, probably about 5 or 6. Once it gets 7 in terms of cubes, that's a little much. Squares, you should probably get up to about 15 memorized. So 1 squared to 15 squared. But cubes, realistically, if you're in a high school math class, probably only need to go up about 5 or 6 cubed. And if you know that, you know 27 is a perfect cube. Now you might be saying, well, what about negative 27? Well, again, negatives, cubes, and fifths, they actually can be negatives. Not on an even root like a square or fourth root, but if you have negative 27 to the power of 3, it actually does have a cube because a negative times a negative times a negative is a negative number itself. So, because I know I can take the cube root of a negative and 27 is a perfect cube, I'm going to apply this second law here because, again, I know 27 is that perfect cube. So I'm going to write it as the cube root of negative 27 all squared. Again, my bottom number in the fraction goes in the notch there. The cube root of negative 27, well, again, I could expand negative 27 to negative 3 times negative 3 times negative 3 all squared. And if you know about your cubes and your fourth roots, this number kind of dictates how many you need in order to extract it out from underneath the radical sign. I need 3 of them, which I have. So I'm going to take that negative 3 out. I'm going to apply that square here, and I end up with positive 9. Now for this last example of the fractional exponent law, we're going to work backwards. Again, equation signs don't always work left to right. They're a two-way street. They work right to left as well. So in this case, I have this one written in this middle expression as well here, and the textbook will often ask you to convert it to a fractional exponent. So we have to consider here, now there's always times where we can assume there's a number in front. So for instance, in x, we assume there's a 1 in front there. All right? There's also something else we can assume with every single number or variable that we don't have to write, but it exists. And it's the power of 1. So I can apply that here. I can say 25 is the same as 25 to the 1. And looking at this law, the bottom number is the 1 in the notch, and the number inside, the radical, goes on the top. So I can say this is 25 to the power of 1/3. So I rewrote it the alternate way. So that concludes all the exponent laws that you would cover it in a high school math course. Make sure you tune into the next video, because now we're going to look at application questions that tie all of these together where the thinking really comes in.